Greetings, my little triglets. Today we're going to talk about section 3.2, and the section has to do with degrees and radians. Degrees you already know about. Degrees, there are 360 of them in a circle. Nobody really knows where they came up with the number 360 degrees in a circle. It's very arbitrary. Some people say the ancient Greeks wanted it to have to do with the sundial and 365 days in a year, but it is arbitrary. Another way to talk about angles is in radian measure. It's not arbitrary. It has to do with the radius of the circle. Now, the best way for me to describe it to you is to actually draw a picture of it. So here we have our circle, and let's say I draw in crisscross lines, and I take the radius, which is this length here, and I take that length, r, and I'm going to put it along the arc here. So both of these red distances are the same. So if I form an angle with how far that red line went, that angle is 1 radian. 1 radian. Now if you continue and you do the circle and you figure out how many length r's can fit on the circle, there's another one, there's another one. There are 3 r's that can fit, and then we have a little bit more down here. That little bit more, if you were to think about it for a minute, is actually 0.14. 0.14 is what's left over in the number pi. 3.14 radians fit in half of a circle. So you might be curious how many degrees 1 radian is. Well, if I take half a circle, which is 180 degrees, and divide it by 3.14, I get 57.3 degrees. So 1 radian is equal to 57.3 degrees. So if you just want a visual for that. But 1 radian basically is the angle formed when the arc is equal to the radius. That equals 1 radian. So if 1 radian, 180, is 3.14 radians, or we can just say it's equal to pi radians. So that means 360 degrees is 2 pi. So drawing our circle, if I were to go halfway around, that would be pi, and all the way around would be 2 pi, or 180 and 360 degrees. So you have to get used to those being the same thing. Now we're going to be able to convert back and forth. We're going to start out with degrees and we're going to convert to radians. So to do that, to convert from degrees to radians, all you have to do is multiply by pi over 180. Pi and 180 are the same thing. It's like our conversion method. Maybe you've done train tracks in chemistry, so it's the conversion factor. So let's do a couple examples. So I have 135 degrees. I want to convert to radians. So multiply by pi over 180. You can do that on your calculator, or you can simplify. I know 45 goes in there and 45 goes in there. So 3 pi over 4. And please put the 3 and the pi on the top. Don't put pi out to the side. It'll make more sense if you keep it together. Now let's just take a look at how that works. So pi, remember, is 180 degrees. If I go 3/4 of pi, that puts me right here, 3 pi over 4. Now let's make sure we know that in degrees. So if I split this up, each of these is 45. So 45, 45, and 45, Add those up, I get 135. So you can see that they do match. If I have negative 90 degrees, multiply by pi over 180, and you get negative pi over 2. Think of that on this circle here, negative half of pi. Remember, pi is halfway across, so negative pi over 2 would be at the bottom, and that's also our negative 90 degrees. So that's converting from degrees to radians. Let's go from radians to degrees. So I bet you can guess that to do that, all you have to do is reverse it and multiply by 180 over pi. So let's take negative 8 pi over 3. 8/3 of the way around. That's actually more than 2 pi. That's because 6/3 would be 2 pi. So we're going more than once around the circle. So we want to multiply this by 180 over pi. Cancel that with that. So I get negative 480 pi. Oops, sorry, the pi's cancel out. So negative 480. We don't need that. So now it's degrees. The pi's cancel out, but the degree symbol stays there. And that's more than once around. Negative 360 would be once around, so that makes sense. Now what throws kids sometimes is if they don't have the pi symbol on there. It's still an angle and it's in radians because it doesn't have the little degree symbol. There is no little degree symbol here. So if there isn't, then it automatically defaults to radians. So you do the exact same thing. It's just not going to come out as neat and tidy. I can still cancel, but I get 480 divided by pi. And if you do that on your calculator, you get about 152.8. So if it's a regular number without pi in it, it's still considered radians, but your answer won't be a whole number. So you have to be aware of that. Okay, one little formula that I want you to know. Remember how we said theta was the angle? If you have an angle, the way to find it in radians is to take the arc length over the radius. S stands for arc length, R stands for radius. Now I like to reorganize or reorder this formula to make it say S equals theta R. And the only reason I do that is so I can remember it, because it spells the word soar. So we're going to soar like an eagle. Beautiful. So the SOAR formula that helps find the arc length. The only big thing you got to remember is it must be in radians if theta is in a formula. Okay, that's why we need radians, is because degrees aren't real numbers. They're a measurement. Radian is the decimal or number equivalent of the degree. So we always have to make sure that we have it in radians if it's in a formula. So put that somewhere big in your notes. Okay, we'll do one example and then we will see how you're doing. So if I want to find the arc length, and I know that the radius is 24.5 centimeters and that the central angle theta is 45 degrees. Write down our SOAR formula, plug in what we know. Theta is 45, however, that's degrees, so I need to write the conversion factor in there right away, and then multiply by 24.5. So if you multiply all that out, you should get about 19.2 centimeters. Make sure you try that on your calculator. All right, I want to leave you with another problem. I want you to figure this one out. Your family owns a big grandfather clock. and it's got a pendulum that swings back and forth. So it's going back and forth this way and that way, and it forms an angle. This angle is 60 degrees. So theta, I'll put a little theta in there, is 60 degrees. And the arc that it swings back and forth, let's see, let me draw it a little bit bigger over here. So this is the pendulum going back and forth this way, that way, makes 60 degrees, and it makes a 5-foot arc because it's a really gigantic clock. So S is your arc length, that's 5 feet. So your question is, I want you to find the length of the pendulum. And do it to the nearest tenth. Okay, so that's what I want you to do and bring into class tomorrow. All right, I hope you all enjoyed 3.2, and remember, always have some trig love. Bye-bye.